multiscale model. Yeah.
Okay, I push just here. Yeah, just tap it. Just press this arrow. Okay. Okay, I will talk about a model that can be used for evaluating urban climate, thermal comfort, wind comfort, and wind-driven rain. Um, it is a multi-scale model, and so we start from the mesoscale, where we use parameterized models, and then we scale it down to what I call neighborhood scale, where we look at heat and wind, and then to the microscale, where we go in much more detail, and we also look at moisture effects. And so that's the level also where we look at trees. I will apply the model to three topics. First to wind comfort, then to wind-driven rain, and finally to thermal comfort. You can ask why I do this. Well, you will see that the wind comfort, that there the methodology already exists for more than 10 years. And I think we can be inspired by this kind of methodology to use it for thermal comfort. The model that I will show is a model that consists of different submodels. First, the wind or the airflow and the buoyancy is modeled by CFD, and here we use a Gauss approach. The radiation includes long wave and short wave radiation, and we use a view factor approach. What I think is quite special of this model is that we also include heat storage in all the urban surfaces, but also moisture. So for instance, if you want to model the wetting of a surface by rain and the storage of moisture in the soil or whatever, this is also possible. And why is this interesting? Because this, of course, leads to evaporative cooling. There's vegetation models for trees and grass, and what is also maybe particular is that you can model wind-driven rain. So you can have a rain effect and see where you have deposition of rain, which can be, again, interesting for evaporative cooling effects, also flooding. You can look where you have most of the rain deposition. And you can also look, and I will show this to you, you can look at durability of building facades. Okay, let's start with wind comfort. In this model, we only use the wind flow, the CFD approach. And I just show you here an example of a high-rise building, standalone, or in a neighborhood with aligned and staggered buildings. And we will do systematically increase the building height and see how the wind comfort will degrade. Why wind comfort? If you have a high-rise building and the wind is hitting the building, you have a downflow, and this downflow will be accelerated by the corner streams. And so you get, as you see, quite high velocity corner streams. And I think everybody knows that if you walk around the building, suddenly you can be hit by those corner streams, and they lead really to wind discomfort. And we did an extensive study for these three situations: isolated, aligned, and staggered. And you see if you increase the building height to the right, you see that these corner streams, the red zones, become more and more important. And of course, the neighborhood around it will or make wind corridors at the left side, at the aligned case, or in the staggered case, it will be more dispersed. This information now you can use to determine the amplification factors. That means how much the wind is amplified compared with the case there's no building, no high-rise building. And this information you can then use and combine with a wind comfort criterion. This is the Dutch wind standard, which is, as I said, quite old already. And it's a very nice approach. It says if the probability that the wind speed of 5 meter seconds, this is above 5 meter seconds, we don't like it anymore. Right? You have also to add 1 meter per second for the turbulence. But if the wind speed is higher than 5 meters per second, then we don't start to like it. And depending on what you do, traversing, strolling, or sitting, you see if the percentage is less than 2.5, it's good for the three activities. If it's higher than 20, it's all poor, and so you get a bad environment. So for instance, if you want to design somewhere a restaurant or space where you can sit and eat, you can look at those criteria. And we applied that to Zurich, so I'm coming from Zurich, and you see here that as long as it is blue, it is quite good. Then you see if the building is at 2H and you go to a staggered configuration, if you would place a building at that position, it becomes deteriorated. And what we see, and this is globally known in wind comfort, if you go above the 2H, so if your building is 2 times higher than the surrounding, you start to have really possible wind discomfort issues. And then, of course, you have to look at mitigation measures. And one of the mitigation measures is trees. I don't go too much in the details, but you see that if you add trees, so left is no tree, then you have trees, that you can modify this amplification factor. So trees are not only good for thermal comfort, they are also good to mitigate wind comfort. Wind-driven rain, I don't go too much into the details, but it's an Eulerian approach. That means you solve the diffusion convection equation in the complete domain, and you do this for separate classes of wind droplets. So you inject droplets and you let them diffuse, and by convection they go in the complete domain, and then you see where they hit the surface. The first step is that you calculate the wind flow. You see you can do this for quite complex buildings. This is here the Parliament building in Ottawa in Canada, which is a copy of the British Parliament in London. Quite complex, and so we try to model that. We first calculate the wind for 8 directions, then we calculate, as you see here, the droplets for a certain size. We do this for different sizes. We make then a catch ratio chart. What is a catch ratio? It says how much more rain you have on a building at a certain location compared to the horizontal intensity. So it rains horizontally, this intensity, you multiply it by the catch ratio, and you get how much rain is coming there. You do this for different wind speeds, for different rain intensities, and then if you have a measured rain event here, history, you can use this information, do the interpolation in your catch ratio chart, and know how much rain comes on a certain location. And here you see how much rain was in the year 2011 on this building. You see most of the rain is on the towers because they get a lot of rain and they have what we call not a lot of wind blocking effect. And you can then, as an example here, we looked in dark color, in black. You see where you have more wetting than drying. And in orange, you see where the temperature, in Canada, you have temperatures below 0, where you can have freezing. So what you see is that you can, by that, easily determine the probability of a risk for frost damage. Last thing, thermal comfort, where we can look at the effect of different mitigation measures like vegetation, evaporative cooling, and cool surfaces. We couple the different models. I will not go too much in the detail, but as I indicated, we have this BHAM model, which is the Building Envelope Heat and Moisture Transport model, which is also coupled. We have different meshes for the air domain, for the radiation domain, which most of the time is an agglomeration of different cells from the air domain. The CFD mesh is very fine. It's too fine for the radiation model. And finally, we have a quite fine mesh for the heat and moisture transport. Why it is so fine? Because you can have rain, you can have really jumps in capillary pressure, you can have suddenly solar radiation that is really drying out. So you see, you cannot make one general mesh for everything, you have to get specific meshes. We use this model also for initial conditions, where we only look at heat. We couple it to mesoscale meteorological models using a blending layer. I don't go too much in the details. We have a porous medium approach for the vegetation, radiation for the vegetation, and also evaporative, transpirative cooling. Last, I just give you an example of a mineral square in Zurich, so there's no vegetation. We studied this during a heat wave. You see here, June of 25th, 2019. And we looked at two mitigation measures. At the left, you see here the artificial wetting of a porous medium by spraying water. So you store water, you use this water, and then you spray it. And we found out that 6 millimeter in the morning is the best to have the highest evaporative cooling effect. At the right, you see some trees that have been planted. So here you see the surface temperatures during the day. You clearly see the effect of the trees. We look then here more in the detail at different times at the surface temperature. You see the reference case on top. Here you see clearly the cooling effect of the pavement that has been wetted, and you see there also the cooling effect or the lower surface temperatures due to the trees. This is at 12 o'clock, I think, and this is at 2 o'clock. And you see that the trees can really cool down more than 2 degrees a zone around the trees, while this evaporative cooling pavement is only a local surface effect. So this is the big difference between trees and pavements. And so our idea is that you should combine them. You can also look at wind velocities. You can see that the trees will slow down the wind velocity. Yes. We can then determine wind speed, mean radiant temperature, relative humidity, air temperature, and we can then calculate the UTCI, and you clearly see the effect of the wet surface here and of the trees. And so you can evaluate different mitigation measures. I have to say all these models that I have shown are implemented in, or we use OpenFOAM as a solver, which is an open domain. And so if you are interested to use this, please contact us. We have 3 solvers. One is the urban microclimate foam. We have one is the wind-driven rain foam, and one is the HAM foam. HAM foam is a 3-dimensional model that you can use for heat and moisture transport in porous materials. And what is special to it, it's physically based. It's validated. Well, I have to say the different models are validated. The coupling of all the models, we would be really happy to simulate with our codes some urban climates case studies and compare with other codes. And I have to say that this you need supercomputing to calculate that. It takes some time to calculate, but what I can say is that successfully bachelor, master, PhD student, postdocs, and senior researchers are using this code. Thank you.
Thank you, Professor Dominique, for the wonderful talk. We have time for questions.